I'm going to be discussing HDL Coder and how it can accelerate your hardware development. A little bit of housekeeping before we start. Please ensure your microphones are muted during this webinar. Secondly, it will be recorded and uploaded to the Opti-Num YouTube page if you want to reference back at a later stage. And lastly, if you have any questions or comments, please put them in the chat and I will address them at the end. A little bit about me. Thank you for joining. My name is Daniela Gersvich, and I am a junior consultant at Opti-Num Solutions. I studied electrical and electronic engineering at Stellenbosch University, and I am super passionate about everything hardware. A little bit about Opti-Num Solutions. We are a management consultancy company who partner with our clients to develop data-driven solutions for complex problems. We are the sole authorized reseller of MathWorks products in South Africa. And you may notice or recognize some of our clients. These include MTN, CSR, and Sasol. So our clients in the work we do spans many industries, including business analytics, financial engineering, mining and manufacturing, digital engineering, as well as the education space. So what to expect today? I'm going to be discussing model-based design in HDL Coder and how you can implement or use them as tools to improve your design and development process, the advantages of HDL Coder, some best practices to follow in order to make your process seamless, and then demonstrate an edge detection and overlay filter model. So a little bit about model-based design. So new technology and the desire to increase product performance has amplified design complexity. And a tool that can be used to make this process simpler is model-based design. So model-based design provides a mathematical and visual approach to develop complex systems. And it has become particularly useful when designing systems to be implemented on FPGAs or like programmable logic devices. Due to its nature, model-based design enables early collaboration and refinement. However, in order to implement these systems on these PLDs, HDL code generation needs to occur. And HDL code generation is the process of converting a model or a script to synthesizable VHDL or Verilog code. HDL code, the HDL Coder app is an app in Simulink or MATLAB that enables this automatic code generation. So now I'm going to just discuss in terms of this design process. Simulink and MATLAB, as I mentioned, will fall under the algorithm and architecture design step within the process, whereas HDL Coder and synthesis tools such as Linux or Xilinx or Intel fall under implementation, where that code gets uploaded to an FPGA or an ASIC device, whatever physical hardware you'll be using. A thing to note about this whole process is that testing and verification is available at every single step in the process. And I'll discuss why this is very useful later on. So the FPGA market or other PLD markets have grown significantly over the last couple of years, and they it continues to grow quite exponentially, actually. So some industries that require FPGA or ASIC design and development include industrial automation, advanced driver assistance systems, as well as high bandwidth communication. And this is just to name a few systems that require this. However, this is not a seamless piece of hardware to implement. And this is shown in this diagram here. So most errors detected during a design, development, and integration process, as can be seen in this image, are introduced in the specification and the design phase. However, these are not necessarily detected so early on and are likely detected during the testing and implementation phase. At such a point, obviously, money has been spent and the deadlines that you may have are approaching. The issue is not necessarily the hardware, but rather the development of the software, such as organizational workflows. And how HDL Coder can mitigate this is through automation of code generation. So HDL Coder, as mentioned, removes the manual process of writing the software and thus possible introduction of errors. So let me discuss a few advantages of using HDL Coder and why it's a super useful tool. So first of all, MATLAB and Simulink give access to pre-existing functions or blocks. So that means not having to derive models or functions from first principles, because that has been already developed by MathWorks for you. This allows a quicker development process. Specialized skills are not required because FPGA, the code required for an FPGA, so HDL, can be generated automatically, and you don't need people with specific skills for the FPGA programming languages. So this allows ease of communication between system architects and hardware designers, as they can understand each other's processes without having to have deep knowledge. Model reusability means that algorithm developers and hardware designers can reuse designs for different hardware targets. So models will only need to be modified depending on the design requirements. So if there are any changes that need to be made or optimization that needs to be implemented. And this will reduce redundancy as well as ensure consistency across models or scripts. Optimization prior to implementation. So as I showed you, testing can be done across all these processes, and thus your models and your final process can be optimized. Then a broad range of microarchitectures. So a hardware developer is not limited to only one specific microarchitecture. They can test on multiple microarchitectures before making their final design decisions. You can generate this production quality code. This generates production quality code. So the code generated by HDL Coder has a high standard and complies with international standards. Functional safety workflows can trace HDL back to the model, and requirements comply with standards such as ISO standards and IEC standards. And then lastly, all of these advantages combined, it accelerates your overall design process, as specific skills, specific tools, and specific functions are not needed to be pre-designed and pre-coded. Some HDL Coder best practices to ensure your process is seamless. First of all, it's important that you start with a clear and optimized Simulink model. So simplify the model, remove unnecessary blocks. This will improve synthesis results, remove blocks that may, or processes or subsystems that may have a singular block that will complete that process for you. And avoid using unsuitable blocks such as those with variable size signals or floating point operations that cannot be converted into fixed point. Secondly, you want your model to be HDL compatible, otherwise you won't be able to use HDL Coder. So it is important that you check this. You can either, prior to your design, check that the block or function you want to use has this topic or heading within the documentation found on the MathWorks website, or as I will show you later, you can check this within the script or model, which has a function that will check compatibility for you. Next is to partition your models into subsystems. You don't want overly complicated, you can use overly complicated systems, however, you want them as readable and easy to navigate as possible. So that's using subsystem boundaries to identify hardware-friendly boundaries. Then verify your model's behavior. So this implies testing throughout all stages of the design process, as I showed in the previous image. So in your design and development phase, as well as your implementation and verification phases, ensure that you've tested that your algorithm or your model is doing what you expect it to do, and then you can compare those results to your results post HDL code generation. And lastly, you want to set your specific target settings. And this is to ensure that you have the settings required for your specific hardware. So this is clock rates, resource limitations, etc. Okay, so that's just a bit of theory and background on that. Now I'm going to step into a demonstration. It's going to be an edge detection and overlay filter, and just some background knowledge on the demonstration. So what this example does, it applies edge detection to this image of the rhino, and then applies an overlay filter, as can be seen here. This is useful in surveillance and security systems, and this is just a single example of where HDL Coder can be valuable, as it has whatever requirements you need for your HDL code, it is able to produce. Now I'm going to step into the model. Okay, so as you can see here, this is the model for those images I just showed you. There are a few steps to the HDL Coder process, but I'm just going to mention some of the things I mentioned previously before I actually use the HDL Coder app. So first of all, I have two branches here. This branch is a simplified filter and overlay, and this branch is the HDL compatible filter and overlay filter and edge detection, sorry. So the one we're going to be generating code for is this pixel stream HDL model. However, both branches do the same thing. Now, this is where the importance of checking compatibility comes in. So in order to do that, I would advise first creating a subsystem. So as you can see here, my model of the code that I will be, or the model that I will be generating HDL code for is within a subsystem. And this is just to check that whether this model is compatible or not. So I'm going to check this branch to see if it's compatible. And this can be done by right-clicking under HDL Code, check system compatibility. Okay, so that's going to take a moment, but yes, so you'll be able to see. So I can tell you now that this model is not HDL compatible. However, this one is. So I will show you. As can be seen here, this is the report back from checking compatibility. It says here, edge detection is not supported for HDL code generation. Edges are not supported. Original frame and this overlay is not supported. So I cannot use this model for HDL code generation. However, this one can be. So your next step is to go into your HDL Coder app or a task. This can be found under apps. Click down under code generation. There's this HDL Coder app. You click on that, okay, and it opens this taskbar. So for the purpose of this demonstration, I'm going to work with the workflow advisor, but I will discuss how you can do it simply if you're experienced and don't feel the need to work through this. So open workflow advisor. Take a minute. Okay, so this is how Workflow Advisor looks. So you have 3 tabs: setting the target, preparing the model, and then the HDL code generation step. So setting the target, it is important. I mentioned it in the best practices. However, for my use case, I am not going to set my target or my synthesis tool, as I'm not linked it to any specific tool, but there are multiple target workflows. You can find documentation about these specific workflows on the MathsWork website. Then the synthesis tool, there's Linux, Altera, Intel, whichever tool is used or you are using within your development. Well, as I mentioned, for my use, I'm going to not just say no synthesis specified. And then setting the target frequency, you can set this to a frequency that you desire. In order to run these, to check that they are correct, I select Run All. Run All will run both of these tasks and give me a correct output or a pass if they are correct. Okay, sorry, let's run this again. There we go. As you can see, that's been passed. So the next step is now to prepare your model for HDL code generation. So this is to check your model settings. So as I checked whether my model was HDL compatible, this can be completed within this step as well. So you can check for blocks and block settings. So you can run each specific one to check the industry standards, model configuration, native floating point, as well as check for ports and subsystems. I'm just going to exit it and run it from here. That checks all those checks, and it is passed as well. And then lastly, the HDL code generation step. So in this step, you can set multiple options under HDL code generation settings. This will open a window that looks as follows. Once again, you can set your target device. I will leave this empty still. So if you forgot to do it earlier or you want to change something previously, you can change it here. Optimization. So this is pipeline. This has general optimization, then pipelining, which is checking your critical path and adding delays between critical paths, such things. Distributed, preserved design delays. There's all specific options. Research sharing, resource sharing. So this is if you want to check which resources can do multiple tasks, and then also check if you need to save space or space optimization, etc. Floating point, I will discuss floating and fixed point a little bit more after this demonstration, but you can either leave your model in floating point or you can convert it to fixed point. Global settings, so these are your clock settings. So you can clock settings, additional settings. You can find more details regarding each one of these settings within the MathsWorks HDL Coder documentation. I'm not going to step through everything now in the interest of time, but it's very useful, and there's a lot of information within that documentation. Now, reports. This is a very important, I suppose, output of the HDL code generation process. And it allows the developers to check the optimization changes that have been made, see where the critical path lies, check which resources are recommended or resource estimation. So it's got lots of positive information. So for my use, I'm going to just tick all of them so I can show an example of all of them. Then if you're going to create a test bench, so a test bench allows for continuous testing, you can select settings based on that here as well. So I'm going to apply my settings that I have changed. And then I'm going to close it. And then I'm going to run this task to check that my settings are correct. There we go. All the options I've set are okay, so I've passed that. So the final step of this process is now to generate your HDL code. So for my demonstration, I'm going to generate a validation model. I'm not going to generate a test bench, and then I'm going to apply. I will run this task, and it will start generating my code. It will take a little bit of a moment to generate the code. A few more seconds. Okay, so not completed yet. with Teams and MATLAB running at the same time. Okay, there we go. And now I have generated a report. So now this is where you can get all the valuable information that helps in the design and development process, especially when you are trying to develop or generate your HDL code. So you have a summary, gives you all sorts of details regarding your model and your settings. Then there's a clock summary and code interface report. Now, an important one, as I mentioned, is high-level resource report. So this gives you all the resources that have been used or the estimation of resources that will be used and the value of the amount of those resources being used. Then there's also detailed report. So it gives you what kind of registers, adders, etc. that are being used. Oh, let me make this bigger. That are being used for your system and where they're being used. So these are the resources used for the edge detection process. So yeah, that's very useful. And if you make changes to your system and you perform optimization, you can see the changes to resources here. Then critical path estimation. The nice thing about this is you can open whichever specific path it is. So you open your model and it indicates the path, the critical path that is. So this is mine. Because my model is super simple, there's no major critical path being followed as there is only one path to follow. But in more complex models, then you will see more detail. Okie dokes, let me go back to the report. And here's all the optimization reports. So frame to sample, distributed pipelining, streaming and sharing, delay balancing, adaptive pipelining, hierarchy flattening, target code generation, code use, and traceability. So I don't have much under these options because I didn't implement any optimization for this example. But when you do, you can step through those different reports to see more information regarding those. So now I'm going to close this and I'm going to open the model where HDL, you can see the HDL generated code. So as can be seen here, it says model block and then pixel stream HDL model. So if I click on that, it opens my generated HDL. This is a very simple example, so there's not a lot of in-depth code in terms of commenting, etc. But this is just something, this is just how the code will appear. Yes, and HDL Coder allows in-the-loop testing as well, or hardware in-the-loop testing. So you'll be able to test this code on your hardware. So yeah. So this is HDL Coder in Simulink. There is also HDL Coder in MATLAB. So if you want more information regarding that, there are lots of resources on MathWorks' website that also give you the step through of how to use HDL Coder within MATLAB. So if you need that, you are more than welcome to go and look at that. Okay, now I'm going to take us back to the presentation. Okay, so I discussed fixed point and floating point. So in my model, I left it in floating point, so doubles, UNs, etc. That's the data type that is. However, and HDL Coder does allow for this. You can leave your model in floating point. Fixed point has higher accuracy, obviously, but it is also more resource intensive. So on the occasion that you do need to convert to fixed point, excuse me, there are two options. You can use the fixed point tool, which is in MATLAB, which is an app within MATLAB and Simulink, or you can manually use convert blocks For this presentation, I'm just going to step through the fixed point tool. However, if you need to understand manually, there are also resources available online, or you are more than welcome to contact me and ask for assistance. So how to find the fixed point tool? You click under apps, as I showed you for the HDL Coder. However, this time you click on fixed point tool. A window will open up like this. A window will open up like this, and this is where you'll be able to see, to select which option you want. So for this example, I use the iterative fixed point conversion, which allows you to select and deselect data types for your model. Okay, so then it will open a window that looks like this. The first step is to ensure, I know it's numbered incorrectly, but the first step is to ensure that you've selected your correct subsystem that you want to convert from floating to fixed point. The next step will to insert an absolute tolerance, so that can be 1 to the 2, -2, or something like that, or 2 decimals, just to see the difference. So whether you're happy, you calculate the difference between what you had and your output with the new data type, and then according to that will output a positive or negative, but I will show you. And then the last step of this page is to prepare. So this collects ranges for your model. No, that doesn't collect ranges, sorry, that just checks your model, and this will be the output. So this one's passed 100%, all things okay, you can move on to the next step. The nice thing about this is your various steps will only unlock or become available once you have passed or completed the previous step. So next is to collect ranges. You can choose your settings, so you can use current settings, double precision, single precision, or scaled double precision. For the example I used in this one, I selected double precision, and then it will collect your ranges. So your simulation minimum and your simulation maximum. And as you can see, the data type is a double. Then you can propose a data type. So what this does is it takes simulation results and calculates what your fixed point data type should be. So as can be seen here. This allows you to accept specific data types. And then once you've accepted those, you move on to the next step, which is to apply those data types, in which case it will change how your model appears. I'm just going to skip ahead to this slide to show you what happens. So this is the model prior to fixed point tool. So as you can see, the input to the subsystem that is going to be used in HDL code generation is a double, and the output were also doubles. However, the fixed point tool will add this data conversion block that will allow for the conversion to fixed point. So the input to our filter is now fixed point, and the output, as can be seen, is also fixed point. However, if you want to analyze the data in form of a double, then it will convert back to a double, as can be seen here. So back to this screen. So now once you've proposed your data types, you can simulate them with the embedded types and compare results. So this will run your simulation. As can be seen, this is the difference, and these are the two results on top of each other. So the previous result with floating point and the result prior to the fixed point tool, and compares. This gives you a match or a mismatch. So this will be based on your tolerance. So for my demo, for my example, I didn't set a tolerance. So as you can see, most of them are failing because the difference is more than expected, which is 0. But as you can see here, the difference is very small by these values. Okay, so this is a super useful tool, very intuitive, that allows for the conversion from a floating point to fixed point. However, certain blocks, which you must also make sure of, do not allow for this, and you will have to do it manually. but the manual process is fairly intuitive as well, as you will just add convert blocks on your own. The only settings that you will need to change are the word length and settings like that, which you can find using a MATLAB function called FIR, if I'm not mistaken. Perfect. So that is everything for this presentation. That is my demonstration of HDL Coder and how it can be super useful in design and implementation of FPGAs and like PLDs, so programmable logic devices. I don't know, does anybody have any questions for me?
Feel free to unmute and ask your question.
Yes, sorry. Yes, Mr. Bernard, more than welcome to ask. Is that an accident?
Sorry, it looks like they can't unmute.
Michelle, I don't know how to do that.
Okay, I can unmute now.
There we go.
Perfect, there you go.
Okay, yeah, my question is in terms of certification, in terms of like RTCA, any similar standards. What's the implication of certifying the hardware for that?
So there is the capability of certifying. They have specific tools within Simulink that follow the process, but also a lot of the, as I mentioned before, the code that has been generated is generally follows these standards. But yeah, for more information, I'm not 100%. I haven't dealt with it myself, the certification, but there are the tools available for that. If you'd like more detailed, I can send you some links or something as well. Yeah.
Yes, if you can send me links, that would be great. Yeah, thanks.
Okay, perfect. If you, maybe just pop your email, or I don't know how. Any other questions? Anything regarding, perfect, thank you so much for your email. Anything regarding the app or the use of model-based design, it is a very useful tool. I don't have experience in HDL code myself. I've never written HDL code, but I was able to develop or create or write HDL code by using the tool. So yeah, it's super useful for that. Perfect. I'll give another few seconds for if you have a question. Okie dokie. So I am going to finish off then. Oh, sorry. I just want to say thank you to everyone for joining. I hope you found this useful. If you have any further questions, and we go back here, you're more than welcome to take my email down and ask those questions, and I'll get back to you as soon as possible. If you just want to find out more about Opti-Num Solutions, here is our website, and you can find what we do and some examples of the work we have done in the past or are currently doing. Thank you very much, and I hope you enjoy the rest of your day. Yeah, thank you. Audrey. Sorry, I didn't see. Okay, thank you.